One way ANOVA is a statistical procedure for testing the difference among two or more population means. Let's look at an example to put this procedure into context. A researcher wanted to know if the type of tutoring affected reading achievement. The experiment involved a sample of 150 sixth grade students who were randomly selected from schools in Virginia. These students were randomly assigned to receive one type of tutoring, either no tutoring, traditional tutoring, or computer-based tutoring. At the end of tutoring, students completed a reading achievement test. The primary research question is, does the type of tutoring affect reading achievement? This experiment has a continuous dependent variable and a categorical independent variable with 3 levels. This design is different than what we had seen before. Recall that an independent samples t-test involves a categorical independent variable with only 2 levels. Now we have 3 levels. How could we analyze this data using methods that we already know? In this scenario, we have 3 groups, and each group has a mean. We could use an independent samples t-test to compare each pair of means, none versus traditional, none versus computer-based, and traditional versus computer. Testing each pair of means in this manner is possible, but it has a major flaw. If we conducted each test at a significance level of 0.05, then the type 1 error rate for all 3 comparisons would be much larger than 0.05. The Familywise error rate is the probability of making a type 1 error in a family of tests when the null hypothesis is true. The equation for computing the Familywise error rate is shown here. In that equation, C is the number of comparisons, and alpha is the nominal type 1 error rate. The table on the right shows the Familywise error rate as the number of comparisons increases. Notice that with 3 comparisons, each conducted at an alpha level of 0.05, the Familywise error rate is 0.143. That is more than double the nominal error rate of 0.05. The problem gets even worse as the number of comparisons increases. If you had 4 groups, there would be 6 pairwise comparisons, and the Familywise error rate would be 0.265 if each test was conducted with an alpha level of 0.05. With 5 groups, there are 10 pairwise comparisons. The Familywise error rate would be 0.401 if each test were conducted with an alpha level of 0.05. This is a major problem. We would like to compare all of the means without inflating the Familywise error rate. The question is, how do we test all of the means and keep the Familywise error rate at the nominal level? One solution is to conduct an Omnibus test, a hypothesis test that compares all means simultaneously. That is, we would like to test an alternative hypothesis that at least 2 population means are different against a null hypothesis that all of the population means are equal. For the tutoring example, the null hypothesis is that the 3 groups have the same population mean reading achievement score. Let's think about this problem conceptually and develop a test statistic. Suppose the participants in each group were randomly sampled from the same population. The box plots in this figure show an example of 3 groups with scores that were drawn from the same normal distribution. That is, the population mean was the same for each group. The population variances were also equal, but the hypothesis test is about the means. The black dot in each box plot shows the sample mean. Their locations are also noted on the y-axis. Notice how the sample means are close to each other. That happens because they all estimate the same population mean. The variability between the sample means is small, especially when you compare it to the variability within each group. The box plots show the variability as the interquartile range, which is the box in each plot. The variability between the sample means is less than the variability within each group. That is exactly what we expect to happen when values from each group have the same population mean. Now let's look at the case where each group has a different population mean. This figure shows an example of 3 groups that each have a different population mean. Notice the amount of variability between the sample means. It is quite a bit larger than what we saw in the previous figure. More importantly, notice the size of the between group variability relative to the within-group variability. The variability among the sample means is quite large relative to the variability within each group. This pattern is what we expect when the groups represent populations with different mean values. This is also the basis of the F-test. The F-statistic is the ratio of between-group variance to within-group variance. It ranges from 0 to positive infinity. There are no negative values, which means that we are only concerned about the upper tail of the distribution. The F-statistic is 1 when between-group variance and within-group variance are equal. It gets larger as between-group variance increases relative to within-group variance. Thus, values of F close to 1 are consistent with the null hypothesis. Large values of F are consistent with the alternative hypothesis. Without getting into detail about the actual equations, the steps for computing the F-test are as follows. First, we partition the total sum of squares into two parts, the between-group sum of squares and the within-group sum of squares. We then divide each sum of squares by its degrees of freedom to get the mean squares. Then we compute F as the ratio of mean squares. Specifically, F is the mean squares between divided by the mean squares within. We then compare the F-test to the F-distribution to make decisions about the null hypothesis. The F-test follows an F-distribution with degrees of freedom nu1 and nu2. Nu1 is the degrees of freedom in the numerator of the F-statistic, which in this case is the degrees of freedom between. Nu2 is the degrees of freedom in the denominator of the F-statistic. In this case, it is the degrees of freedom within. There is a different F-distribution for each different set of degrees of freedom. However, F-distributions are positively skewed. When the null hypothesis is true, large values of F are rare, and that is evidence against the null hypothesis. We can obtain critical values from the F-distribution by using computer software or a table in a statistics textbook. P-values can only be obtained with computer software. Statistical programs will provide the p-value of the F-test in the output when you run the analysis. One-way ANOVA is an extension of the independent samples t-test. As a result, the F-test in one-way ANOVA has the same assumptions as the independent samples t-test. We assume independence, normality, and homogeneity of variance. Let's return to the tutoring example. One-way ANOVA is the correct method of analysis because we have a continuous dependent variable and a categorical independent variable with 3 levels. The research question was, does the type of tutoring affect reading achievement? This leads to a null hypothesis that the population mean reading achievement is the same in every group. No tutoring, traditional tutoring, and computer-based tutoring. The alternative hypothesis is that at least 2 population means are different. We will conduct the test at a significance level of 0.05. Analysis of variance tests are reported in a standard table format. This table shows the sum of squares, degrees of freedom, mean squares, the F-test, and the p-value. Most statistical software will produce output in this format. Here we see that our F-statistic was 17.67 and the p-value is less than 0.001, which is well below our significance level of 0.05. Therefore, we reject the null hypothesis and conclude that at least 2 groups have different population means. Although we know that at least 2 population means are different, we don't know which ones they are. We don't know if it's between no tutoring and traditional tutoring, or between traditional and computer-based tutoring, or between no tutoring and computer-based. We don't know which comparison is the significant comparison. That means we have more work to do. If we reject the null hypothesis, we must conduct multiple comparison procedures to identify which groups have different population means. Multiple comparison procedures allow us to conduct pairwise comparisons and keep the family-wise error rate at the nominal level. There are many different multiple comparison procedures. 3 popular methods are Bonferroni's procedure, Tukey's HSD, and the Holm-Bonferroni procedure. You will learn more about multiple comparison procedures in another video. In summary, One way ANOVA allows us to conduct an omnibus test of the null hypothesis that two or more population means are equal. If we reject the null, we know that at least two means are different, but we don't know which ones. We conduct multiple comparison procedures after finding a significant F-test. Those methods allow us to determine which population means are different,